welcome to 7.3 Similar Polygons. Your goal today is that I will be able to recognize and draw similar polygons and use their properties to solve some problems. A polygon, poly means many, so that just means having multiple sides. If we take a look at this diagram here to our left, we have a rectangle ABCD. Okay, we have two dimensions here. You get them just by finding the side lengths with a ruler. I don't have a ruler on me right now, so I just made an appropriate size dimension. So we have 3 centimeters from the width, from A to C, and C to D is 5 centimeters respectively. So that means this would also be 5, and this over here would also be 3. So if I want to put in the length of AB, which would be the length from A to B, that would equal out to be 5 centimeters. BD, 3 centimeters, and so on and so forth for the other corresponding sides. Now, when it comes to a rectangle, all degrees are actually 90. All degrees in a rectangle equals 360, and that makes sense because 90 times 4 would be 360. We have 90 degrees. And if I didn't know how to do this, I could definitely use a protractor to figure out that this corner angle here would be 90 degrees. Now we have this shape, and now we have another rectangle here. It has A with a little apostrophe up at the top of it. This is actually called A prime, okay, meaning there's been one change. If we made a second change to this rectangle, so let's say we have this rectangle here, we have A prime, B prime, C prime, D prime. If I wanted to make a really small rectangle, I would call this A prime prime, or A2 prime, B2 prime, so on and so forth. So, comparing that, assume this actually has a scale factor of 3. So if this is a scale factor of 3, just going off of our notes from earlier on, this would be multiplied, this length would be multiplied by 3. So now I would have 9, because 3 centimeters multiplied by 3 gives me 9 centimeters. And this length here would actually be 15 centimeters. So now I can go ahead, I can fill out the rest of this chart. So we have length from AB, it's right here, so we have 15 for AB, centimeters of course, 9 centimeters for BD, 9 centimeters also for CA, and 15 for DC. Luckily all my angles stay the same. If I were to measure out those angles, it would all still be 90 degrees. Those are the properties of a rectangle. Now, it's asking us, now that we have that completed, what can we say with respect to changing this altogether to a scale factor, or by a scale factor of 12.4, making an even huger rectangle. So, I could take my original dimensions. This is what it's talking about, my original dimensions, and multiplying those by 12.4. The reason why I know it's my original dimensions is because see how I have prime and prime, just like I did for this one. So it means I'm making one change from the original. Okay? It's always in relation to the original. So instead of 3 centimeters, I would have 37.2. So this would be 37.2 centimeters. And then instead of the 5 centimeters, we'd be able to multiply that again by 12.4. Figure that's 62. So we would have 62 centimeters, 62 centimeters, 37.2 centimeters. And luckily, where this is not really changing in shape, properties of the angle remain the same. What do we notice here? So although the scale factor changes the length of the sides, the angles are actually still the exact same. Because if you think about it, you didn't really change the proportion ratio of anything. You made it bigger, or you could make this smaller, of course. But the exact relationship with the angles, the length of the sides, really affects the angles. So if you made a specific change to one side, you're going to change the angles. But here, we made this exact same side change to all sides. Therefore, the angles are not affected. So if we take a look at this shape here, this polygon, it's not a pentagon. What you should first off try to do is label the sides. So we can just start off A, B. You're going to try and be sequential. You're going to label them at the vertices. If you don't know what the vertices are, these are when the two lines meet. This is like the corners. A, B, C, D, E. Okay. So now I have to find out the lengths, and then I also have to find out what the angles are. Luckily for me, I know that if I'm talking about the lengths and the sides, I can talk about A, B. So that's that. I can talk about B, C, C, D, D, E, and then E, A. You can just use the two letters, and if I put E, A or A, E, not correct or not incorrect at the same time, right? Like it's just the exact same thing. E, A is the same as A to E. So I can measure these sides, and if I want to even think about the angles, so angle A, angle B, angle C, angle D. I do actually have, like I said, two angles I know of already. Angle D is a right angle, angle E is a right angle. Therefore, these are both 90 degrees. And now what I have to do is I need to find a protractor to figure out what is this angle. Obviously right here, this would be 90 degrees, so this is a little bit more than. I'm not sure if that is 90 degrees. It kind of looks like it's close to, but I think it looks like it's a little bit less. And likewise here, this is greater than 90 degrees. But what we'll have to do is we'll have to go and check that out. And the actual question that I've taken this from would be this one here. So I wasn't able to fully replicate the polygon, but this is right out of the textbook in chapter 7.3. And what happens here is later on this does get enlarged, so that although all of these numbers change, let's say these are all doubled by 2, doubled by 2, doubled by 2, so on, for all the sides, we're going to notice that the angles are still going to stay the exact same. That's what's kind of different about similar polygons. So what I would advise that you do is I would just finish up this section here with saying corresponding angles are actually equal. So if you change the size of a shape, the angles stay the same. Corresponding sides are proportional. So the side lengths change. Okay? However, the angles are the same. And all sides are proportional. So if you multiplied one side by 4 or 5, you multiplied the other sides by 4 or 5. Okay? So if polygons have these properties, we say these polygons are similar. If they didn't stay the exact same, so let's say, for example, I have a triangle here. If I have a triangle, and it's an equilateral triangle, so this is 60, this is 60, this is 60. And let's say I have 7, 7, 7. But for some reason, when I redraw this out, this side's 8, and this side's 9. Well, 7 times a number won't give me 8, and 7 times the same number won't give me 9. Therefore, this is not a similar shape or similar polynomial. I would need, in fact, there to be a bigger triangle, and it can be like, oh, this is 21, this is 21, and this is 21. So 7 times 3, the scale factor here would be 3. 7 times 3 would be this 21. 7 times 3 would be this 21. Therefore, this would be 60. This would be 60. This would be 60. These sides are proportional. Those angles are the same as the other ones. Okay, so that wraps up 7.3.